Then next one will be the EMF equation of a transformer. So let us consider N1 as the primary turns and N2 as the secondary turns. So phi m is the maximum flux linking with the core. So where if phi m is given by Bm into A, that is Bm is the maximum flux density in the core and A is the area of cross section. Let F be the frequency in Hertz. So as we know that the flux will vary sinusoidally. It will vary from 0 to maximum, then to a minimum, like that. So if you consider the full cycle, this is 0 to 2 pi will have. For one cycle, whatever the frequency is, once complete one cycle, the time taken will be t. So we know that frequency is given by 1 by t. So considering that a t will be equal to 1 by f. To reach the maximum, you can see for the complete cycle, it will be a frequency will be 1 by f. To complete the maximum, the time taken will be 1 by 4f. The average rate of change of flux is given by, so obviously from 0 to maximum it is changing, 0 to a maximum. So the average rate of change of flux is given by phi m by the time. So here the time will be 1 by 4f. So if you simplify that, we are going to get the equation as 4f phi m. Therefore, the average EMF induced per turn is given by 4f phi m in volts. Now, if you want the RMS value, so as we know that the relation between the RMS value and the average value, so your RMS value is given by average value into a form factor, where form factor value will be 1.11. We have already derived the equation for the average value in case of a transformer. It will be 4f phi m. So the RMS value of induced EMF per turn is given by 4.44 f phi m. Then the RMS value of the induced EMF is on the complete primary winding. So if you want to calculate the total RMS value, we should multiply with the winding also. So that's why we are going to multiply the number of windings with respect to that. So the equation now will become 4.44 N1 f phi m. Either we can keep this one as a final equation, or we know that what is phi m. Your phi m is given by a maximum flux density with respect to a particular this into a area. So you can replace the equation phi m by Bm into A. So it will become 4.44 N1 f Bm into A. Similarly, you can write the equation for E2 also, which is given by 4.44 N2 f Bm into A in volts. This is the EMF equation for a transformer. Then what are the different types of losses which will occur in a transformer? So if you consider a transformer, there will be majorly two losses. One will be the iron loss, which is also called as a core loss. Another one will be the copper loss. Core loss. So the core loss or the iron loss is due to the alternating flux in the transformer. The flux remains constant for all the loads. So that's why these losses will vary from 1% to 3%. Again, the constant losses can be divided into two parts. One is hysteresis loss, another one is eddy current loss. If you consider with the hysteresis loss, since the flux in the core is alternating, there will be a continuous reversal of a molecular magnets are required. Because of this, there will be a heat will be dissipated, which is called as a hysteresis loss. And the equation for the hysteresis loss can be written as P into B max to the power 1.6 F in watts, where P is a hysteresis loss constant. And as we know that B max is nothing but a maximum flux density, which will be in Weber per meter square, and F will be the frequency. If you consider with the eddy current loss, again this is due to the core loss was present in the core. Again the flux will be alternating in case of a core. So where because of alternating flux in the core, it will be creating a circulating current inside that. So because of that, energy will be dissipated in the form of heat. This circulating current, whatever the circulating current is there, because of that the energy is lost in the form of heat. That is called as a eddy current loss. So this can be minimized by using a laminations, what we are going to use between the sheets. So using this laminations, we can reduce the eddy current loss. So and the eddy current loss is given by Q, which is a eddy current loss constant, into B max square into F square. So if you consider the eddy current loss and the hysteresis loss, it depends on the supply frequency and the flux density. So that is the formula, if you remember, for the eddy current loss and the hysteresis loss. For the hysteresis loss is proportional to B max to the power 1.6 into F, but hysteresis loss is proportional to B max square into F square. It depends on only on the supply frequency and the flux density, and these are independent of the load, so it will not depend on the load what we are connected. So that's why these are called as a constant losses. Next one will be the copper loss, or also called as a I square R loss. Since the resistance is present in the both primary and the secondary, we will be using the winding material as a copper or aluminum. So obviously it will contain some resistance. So when current passes through that resistance, we will have a I square R loss. So in the primary, we will have the current flowing will be, let us assume, as I1, and the resistance present is R1. Similarly, current in the secondary is I2 and the resistance is R2. So the losses will be I1 square R1 in the primary winding and I2 square R2 in the secondary winding. So the total copper loss is given by primary winding loss plus the secondary winding loss. And here majorly the loss depends on the value of the current flowing through the windings. So that's why it is dependent on the load. Whenever there is a load will be present, right, the current flows through the circuit. So whenever we are connected with a higher load, obviously there will be losses, current flowing through that will be more, so losses will be more. If the load connected is with a lower value, obviously current flowing through that will be less and the losses will be less. Hence it depends on the load, so it is a variable loss. That's why the copper losses are the variable losses. So here you can observe, as the load increases, loss is also increasing. Then efficiency of a transformer. So you can consider whatever efficiency. Efficiency is nothing but whatever the effort we are putting and whatever the output we are getting, that is called as efficiency. So with respect to electrical term, if you are going to consider, it is the ratio of output power to the input power. So let us consider output power as it is. The input power is nothing but output power plus the losses. So losses are of two types, already we have discussed. One is with the core loss and another is with respect to the copper loss. So that's why we can replace your input by output power plus core loss plus the copper losses. So output, if you are going to consider, since we are considering secondary as the load connected, so secondary side, what all the voltage and the current we are going to get, it will be related to the output. That's why we can write the output equation as V2 into I2 into power factor divided by output power, which is V2 into I2 into power factor plus the core loss plus the copper loss. Copper loss which will be included for both the primary and secondary, so it will be I1 square R1 plus I2 square R2. Then load corresponding to a maximum efficiency. So here, if you are going to consider, if you want to rewrite the equation for the transformer efficiency, we can write, so it depends on the load. So if the load is 100%, we are going to take X value as 100. If not, it's variable, we should include the loading also. So your efficiency equation can be written as X into V2 I2 into power factor divided by X into V2 I2 power factor plus the iron loss plus X square into the copper loss. So as the load varies, obviously our output also varies. That's why along with it is directly proportional. That's why we are considering the load X along with the output. And your iron loss doesn't depend on the load. That's why we are taking as same itself. But if you consider with the copper loss, the formula is I square R. As the load varies, the current varies square of that. That's why your copper loss depends on square of the load. And to calculate the maximum efficiency, we should calculate the what should be the load at the maximum efficiency, which is given by X is given by the full load kVA into square root of iron loss by copper loss. By using this we can calculate, so what is the percentage of load at which we can achieve with the maximum efficiency.